All right, watch. So, are you ready to take a look at? Now, sometimes the other thing we should stop to say too is that a lot of times rectangular polar form, one or the other, is more advantageous, right? So you can see that, for example, on B, you might prefer the rectangular form. Isn't like y equals 2 more illuminating than the original equation? Yeah, you might be like, yeah, I think we could agree with that. For A, you might say the opposite, that like the rectangular form is actually kind of messy. So let's take a look at what that graph looks like. I'm just going to assume that Shoma is right. Is that trust? Okay. How am I doing? Did I get it all in there? All right. All right. So this is the plot of what he said here. Hey guys, this is the plot of what he said. There it is. Okay. And then let's just, for comparison's sake, let's type in r equals 3 minus 2 cosine theta. Boom.
Wait, so does the theta not matter next to r?
Yeah, it's a function. R of theta. It's like y. It's like f of x or something. Do you see how that red graph and the blue graph land on top of each other? You know what that means? It means you're right. Good job, right?
Wait, just in case, is it possible to explain the weird thing?
Absolutely. In fact, that's going to be the entire project of today's lesson. Okay. All right. Any other comments around our homework / yesterday / life? If not, let's actually do that. Our goal today is without a I mean, we'll go to the calculator as well, but our goal would be to analyze some of these polar graphs without ever going to rectangular or anything like that. In fact, it's not really that helpful to go to rectangular. On that first example, if I want to like analyze the behavior of that graph, it's not like after I get it into rectangular form, like, oh, it's just x equals 1 squared plus y squared minus 3 times the square root of x squared plus y squared equals 1. Now I know what it looks like. Oh wait, no, right? So let's see if we can look at a couple examples of polar functions and graph them just from first principles, like empirically. Let's graph a few points and see what we get. So I'm going to ask a couple of you. This will be a good trigger of you. I'm going to ask a couple of you to just evaluate this function that I have up here. Add a couple theta values. No calculator needed. Just please do it in your head. I'm going to ask you when I do this to evaluate it at 0 and at pi over 2, at pi and at 3 pi over 2. That is like the fourth cardinal directions. So Thomas, Haley, Alex, and Kate, you're going to do that for me. Thomas, would you give me the value of this function when theta is 0? What is r when theta is 0? When you're ready. Everyone else should follow along too. What is it? 4. Yes, do you agree? If you plug in theta equals 0 that you get for r, 4. Yes? Okay, so that, remember polar coordinates, what that means is in the 0 direction, we're going out 4 units. Yay. Okay. And then Haley, could you evaluate this when theta is equal to pi over 2? What happens when theta is pi over 2? What do you get for r? I'll give you a second. So 2 times pi over 2 is pi. Cosine of pi. So what does it come out to in the end for r? -4, right? Yeah. Yay. Okay. So that means, let's review what that means too. Pi over 2, if theta is pi over 2, then that means we're in this direction, but wait, if it's -4, that means we march backwards to there. Yes? Okay. Alex, give me the value when theta is pi. When we're in this direction, what is r when theta is pi? I mean, work it out actually. What do you get? Cosine of 2 pi is what it would be then, I guess, right? Plug in pi here.
Yeah. Okay. So it would be
4. Yes. So in the pi direction, we're walking forward 4 units to there. Well, assuming that you're in this direction, you're pointed in this direction, you're walking that way 4 units. Okay. And then Kate, if you give me, what about 3 pi over 2? What happens if theta is 3 pi over 2? Yeah, so if we're pointed now again for Daniel, we're pointed this way, but since there's -4, we're walking backwards. So we're here. All right, did you catch where we were at different times? We were here, and then the next thing was we were here, and then we were here, and then we were here. That's kind of a little confusing, maybe. Let me ask you one other thing. The domain of this is all reals. The theta can take on any value. We're going to allow theta to be anything. What is R? What's the range going to be? What values of R are possible here? You just kind of said them. What? Yeah, no, -4 is the lowest and 4 is the highest. Could R ever be 0?
Sure.
I think so. Can you actually demonstrate? Tell me when it is 0. When would that happen? When will this be 0? Well, when cosine of 2 theta is 0, when does that happen?
It has to get pi over 4.
Pi over 4. I like hearing that. Why? Because pi over 4, if you plug pi over 4 in, you'll get pi over 2. Cosine of pi over 2 is 1, is 0, and times 4 is 0. Okay. So it will be 0 at pi over 4, and at actually the other over 4s, I think it will be 0 as well. Good. So again, let's pay attention to how this was drawn. This is like handwriting class. You want to not just draw the right picture, you want to do it with the right stroke in order, just so you, not because after looking at your text I'll know, oh, you drew it in the wrong order. I would never know that. But just so that for your own comprehension, you understand, like, for the various theta values as we go around, how this is actually being drawn, what R values get produced. So we started here, right, for theta equals 0. And then we swept through there at pi over 4. Now at pi over 2, we're actually way down here, right?
Oh, can we keep going back?
Okay, don't criticize. That's something like that, right? Okay, it should be going through. So that's the order in which it's drawn. If you want to graph it on your calculator in polar mode, you'll type this in, and then you'll do 0 to 2 pi or something like that, and it'll draw this picture and watch it. It'll actually do it in this order, right? And it makes sense based on what we just stepped through. I just asked you guys theta values, and you gave me R values in that order. Yeah, Justin.
Is that because it's at 0 at when it's 7 pi over 4 and all of them?
Yeah, at all the pi over 4s, it's back at 0. Yeah, so it comes back home every 90 degrees. And what else was I going to say there? Oh, and then of course after 2 pi, it repeats again, right? So you could watch
So it would
this.
just be the same thing.
Yeah, yeah. Stella, did your question get answered too?
I was gonna ask, will we get sense of if you like draw this, will we like something wider or?
No, I mean this is good. As long as I have like these 5 critical points that I've just labeled, like that are really clearly on there, I think that we're okay. Okay. So that's beautiful. Yeah, like I said, feel free to graph it on your calculator too if you want. Feel free to also, if you like, just for fun, convert this from polar form to rectangular form too, right? That would be fun. But not necessary in order to analyze these graphs. All right. So these kinds of curves, the one we just looked at and the one we're about to look at, are called Rose curves. So this is like this is an analysis of what we've just done, but I always hesitate to give the rules really at all, just because I think it's better to do what we just did. Did you sense us using any rules per se? Not really. We just plugged in some values and figured out in each of the cardinal directions what's going on. I kind of tried to get a feel for the graph. I like kind of more fundamental level. Don't memorize these rules and then be like, okay, well if it's cosine, then that first petal is going to point to the right. Oh wait, no, was that sine? How about you just like kind of know what you're talking about rather than like trying to memorize a rule, right? Is what I always kind of default to. Now there is something interesting that's said here, right? This is the case we were just in. If we have a 2 theta in there, you saw the last example was a 2 theta inside, right? Then you get 4 petals. You saw that happen. If there's an odd number in there, it's like 3 theta, like the one we're about to do, then you get, how many petals is this going to have? Yeah, it's actually going to have 3 petals. And I need you to start thinking of, we'll answer this question before you leave today, but I want you to start thinking about why would there only be 3 petals? That seems really weird and arbitrary. And mathematics should be like a sense-making discipline. Doesn't seem right just because I said so. So I did tell you that, but I want you to justify why that's true. Of length, oh, the board is failing me right now. 3. So that's what we'll see here. And again, I want you to be thinking in the back of your mind, why is that happening? That why don't we get 6 petals? The last one seems like that was what was happening. And how would I get like 2 petals? I mean, is there a way to do that? I don't know. Think about these things. All right, that's not the only consideration we have is 3 petals of length 3. Now, don't graph this with your calculator or anything. Let's do this by hand again. I know. And we're not done with that. We also need to figure out where they occur, right? So I think I understand there'll be like 3 equally spaced petals of length 3. But if I can just find one of them, then I'll be good. So what does it mean to have like a petal on this graph per se? Well, it means that R has reached its maximum or minimum value, right? Like, isn't that where those tips, what those tips represented on the last one is like? Yeah, so I'd be interested here, for example, I'd be looking for when R is 3, right?
Yes.
When would R be at its maximum value? 3 theta.
When sine equals 1.
Or plus or minus 1, right? Yeah, plus or minus, we want sine to be at its maximum. So when does that happen? What does 3 theta have to be?
Pi over 3. No. Pi over 6.
Yeah, so 3 theta, I mean, the sine function normally has its maxes at pi over 2 and negative pi over 2 and 3 pi over 2 and things like that. So it's an infinite number of places where these happen, right? But all I just need to do is find one petal. So 3 theta needs to be pi over 2, so what would theta have to be? Sue said it already, but yeah, pi over 6. Okay, and there are other petals too, but I just wanted to locate one of them just so we can like nail down one of them at least. I think one of them is at pi over 6, right there. Okay, good. By the way, you can go back into the original equation, you can plug in pi over 6 and see that you do in fact get 3. Try it, you're welcome to, right? 3 times, oh yeah, that's pi over 2, sine of pi over 2, 1. Oh yeah, 3, good, yay. Good. Where's the other petals be then? Keep in mind that there will be 3, and maybe we expect them to be equally spaced. I don't know. So, how might we locate the other ones? Yeah. Pi over 2? Maybe. Okay. How'd you come up with that? Good. Yeah. So pi over 2. That's a little tricky. Where does that actually go though? Do I do a petal here, right here? Plug in pi over 2 and see. What do you get there? Yeah, because you get 3 pi over 2. Sine of 3 pi over 2 is negative 1. So yeah, you'll get negative 3. So one of them is down here. Like I said though, if you know there are going to be 3 equally spaced petals, how else can you like locate them too if you want? There's also one up here somewhere. Is this going to be 1 too? Is that what you're saying? I don't think so.
3 pi over 5 pi over
If they're only going to be 3 petals, thank you, Sue. It is 5 pi over 6. How often are they spaced then? Yeah, a third of the way around the circles, 120 degrees. I heard someone say, or if you're in radians, it's even easier. It's just 2 pi, a third of that, right? 2 pi over 3 radians. So yeah, a couple different ways to say it. So if you find one petal and you know there are 3 of them, they're equally spaced, you can just add 120 degrees to get to the other ones. Does this go through the pole again? Yeah, we could even figure out when that is. I think what we'll find is we get a picture like this. Yeah, that goes in order too. Notice I started here at the origin, because if you plug in 0, you get 0, don't you? So right away at theta equals 0, you're here. And then by the time you're sweeping toward pi over 6, you're out here. And then by the time you're at pi over 2, Isabel told us we're actually down here. Okay? So that would be the order that's drawn in. Yeah?
Will you always give us on the circle graph?
I think I do usually give that to you on the test or something, but you don't need it, and you can draw it however you like on your notes. I'm still curious about this whole rule up here, though, right? So I'd like to answer that. Yeah.
I was just going to ask, like, if we were to convert something that is has rectangular.
Hey guys, I would like to hear Matthew's question.
Is like
From rectangular.
rectangular on the rectangular graph. If we converted it to polar, it wouldn't be equivalent because of the peaks?
No, I mean we can get this in rectangular form, I think. In fact, I think we did do one of these yesterday.
I just mean if we have like a rectangular equation that goes off to infinity.
I'm having trouble understanding your question.
Do these go on forever? Can you do how after you hide this
Oh, no, it doesn't repeat after two. I mean, after two. Yeah, it'll come back onto the same color.
So it would go off into
I mean, it goes off to infinity and comes back though. It comes back from infinity too. Yeah. All right. Are you ready to graph this on the calculator? Let's watch this, and I need you to watch this carefully. Okay. I'm gonna put this in sine of 3 theta. Window theta goes from 0 to 2 pi. How about? Okay. Yes. Good. We ready? Watch it. Okay. Now I want you to watch this carefully. I'm going to use, just so you can see it really clearly, I'm going to use this ball and track mode and path mode here. You ready? And watch carefully. Just exactly as I said, it's drawing it that way. Watch though. I only said 0 to 2 pi, but what's happening?
It's going again.
It went around twice. So how many petals are there again?
6.
I mean, really, there are kind of 6 petals, aren't there? It's just the second set land right on top of the first, and it has to do with even and oddness.
So are we still using the?
If you change it to 4, we expect only 4 petals. But notice, again, I still 0 to. Oh, sorry.
So always do it.
How many petals was that going to be?
8.
8, yeah. Sorry, I wanted to illustrate with the last example, kind of this science that goes
They're
on.
all 2 ended.
So there are, yeah, so I have an even number in there, and this time I'm getting 4 petals, but as we go from 0 to 2 pi, it only, watch what it doesn't do this time. Right, it only draws it once. So so maybe there's some sense making there, finally. I have more to say, obviously, about that. In fact, I might ask, what if n is not an integer at all? What happens?
It doesn't work.
It doesn't work. You actually get some pretty pictures.
You
Okay.
get one over, like, partially.
Yeah, they may overlap. I have some questions about what kinds of numbers n could be, and how that would work. This could get really interesting. Yeah. Let me put it back to the other one we just looked at. Isabel, go ahead. Sorry.
So my question was like, so for the maximum of 3, right?
Huh?
Like one of them is from pi over 2, and one of them is from negative pi.
Mhm.
Where's the third one from?
Well, okay, so these get generated at the following values. At pi over 6, we get one. At pi over 2, we get another one. This one down here.
Yeah.
And this one is generated at 5 pi over 6. Actually 5 pi over 6.
5 pi over 6.
Plug it in. Times 3 is
Oh.
5 pi over 2, which is what?
Oh.
It's just coterminal with pi over 2 again normally, if you think of it as, right? Okay. So yeah, so this is only, if you want, you can draw this in only a space of 0 to pi if you like, right? So 0 to pi, we can just range through those theta values and we get the whole thing. How would we get just the first petal? What if we just wanted to draw the first petal? What theta values would I want? How about 0 is when it started. When do we get an R value of a second time of 0? If you solve it, if you set 0, R equal to 0, and solve, yeah, you'll get pi over 3. Right? So there's just one petal, right? All right. Lots of cool stuff happening there. I'm going to skip. I have like these rules for limacons that I just copied from your book. This is the next pretty picture we're going to look at. But we're going to skip that. It's just right from the book. But I'd like to take a look at these graphs now. I really don't like the rules. I'll show you them in a minute, but I'd rather just graph these from first principles. Again, these are called limaçons. It's a French word meaning snail, and that's a circumflex under the C. You got to be fancy like that, and you also have to say it like a French person. Limaçon. You have to say ha 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 afterwards. Right? Channel your inner Mr. Giron.
It actually sounds good.
Okay, Mr. Giron. Okay. All right. Again, I'm gonna pick on 4 people here to give me trig values. I'm gonna ask for the cardinal directions again. Teo, Amy, Jeremy, and Sue. Teo, can you give me? Teo? Where are you, Teo? By Teo I meant Eric. Can you give me, Eric, when you're ready, the value of r when theta is 0? And the others will be giving me 0. Theta equals 0. What is r? For this first one? Yeah, because sine of 0, that whole part, the second whole part goes away, kind of, right? Yeah. So we get 1, 2, 3. When theta is 0, r equals 3. I agree. Amy, what about when theta is power 2? What do you get? Yeah, because this actually is 1, so it's 3 minus 2. I'm with you. Okay. And then Jeremy, can you get me for pi? What about that? If theta is pi. What is r? 3, because again, like 0, this goes away here, right? 1, 2, 3. Yeah, good. And then Sue, what about for 3 pi over 2? What would the r value be? 5. Yes. So again, we're letting theta range over all real numbers, if we like. What's the range, though? That's the domain, all reals. What's the range? That is, what's the lowest and what's the highest r value that we could get? 1 is the lowest r value, right? We heard said. Just think about this expression. Don't think about the graph yet. Just think about this expression. The lowest number it could possibly output is 1, and the highest is 5, right? So that tells me that if you're thinking about the range on the graph in Cartesian coordinates, you're often thinking about kind of 2 horizontal lines that it stays between or something, kind of, right? Well, here, this stays between these 2 circles, right? Like the entire graph that we're about to produce, which you haven't even seen yet, but I know it will be completely contained in this annular region, right? It'll never go outside this circle. It'll never come inside this circle. All right. So let's graph it. Here it goes. It looks something like that. Well, I want you to think about what is the maximum and minimum of sine. Yeah, this can only be as big and as small as negative and positive 1, right? So now talk to me about this whole expression. Could r ever be 0? Could this expression, 3 minus 2 sine of something, ever be 0? No. The smallest we could get is this being negative 1, which would produce the number 1 only. All right, so there's a picture of your first limaçon. Your first limaçon. It's beautiful. Snail, by the way, snail, I hear you say, isn't that escargot?
Yeah, it's
But that's dead snail. This is a lie. I'm serious. I'm being serious. Escargot is snail that you eat. it's like chicken versus poultry or something, right? Okay. That makes sense? Yeah. Or pace versus pescado. Yeah. In Spanish, that's right. All right. 2 plus 4 cosine theta. Again, I'm going to pull 4 volunteers, and by volunteers I mean people I choose. Okay? For the cardinal directions. George, can you give me 0? And then Daniel, Daniel and Anna and Matthew are on deck. George, can you give me for this one over here now on B? All right, George. Sorry. 0. B 6, because this is, I think I'm with you. 1, 2, 3, 4, 5. That's unfortunate. We'll just put it there. Daniel, what about for theta equals pi over 2? What do you get? 2? Yes. Anna, what about pi? Yeah, interesting, right? So when we're in the pi direction, I gotta think this through. I'm actually back here. Okay? And Matthew, what about 3 pi over 2? If theta is 3 pi over 2, what's cosine of 3 pi over 2 is?
-2.
Cosine of,
0. I'm sorry, 2. I thought about this and then I was figuring out pi.
you got it. All right, and then here's another question. Will theta ever take on the value 0? Excuse me, will r ever take on the value 0? What do you think? Let's talk about the range again. What's the lowest r value we just talked about? What's the highest? Lowest and highest? Yeah, -2 to 6, and maybe it takes on all values in between, right? So maybe it's 0. In fact, could you show me that it's 0? Could you even tell me what theta value gives me an r value of 0?
Yes.
Actually, here it's nice, isn't it? What theta value has a cosine of -1/2?
It's 5 pi over 3. Oh, something over 3.
How about 2 pi over 3, or 4 pi over 3 also? All right, so are you ready to draw this one? Here we go. This will be fun. All right, so both of these are considered Lima songs. Okay, guys, this one has no inner loop and doesn't even touch the pole at all. This one does have an inner loop, and the size of that inner loop is dictated in the way that we talked about, right? What is the lowest and the highest r value you get? If you're low, you have a -2 for that's your inner loop. And 6 was our biggest value. That's the size of the outer loop. And I also want you to think maybe too, I know we're coming to the end here, but I also want you to think about how this graph looks like, thanks guys, from last semester, right? And how that relates maybe. We'll talk about that a little bit more tomorrow, I guess. All right, by the way, these rules are in your book. I just copied them. If you want to take a picture, you can.